Okay, so today's going to be a little bit different because I'm going to present a model, but then I'm going to talk about some code and actually do do the model as an event graph. Then I'll show you implementations in both Java and for those who are using Python and Python as well. So I probably won't get to the entire just in terms of time. Normally I'd have time for this extra model, which actually is it just illustrates another aspect of using event graphs and handling resources. I don't think I'm going to get to it today because I'm going to be covering both the Java and the Python implementations of what I'm going to be implementing. But this is about transient entities. And what we've seen in the last couple of models is first of all, using a container as a state variable and then putting stuff in, taking stuff out. So the state of that container is part of the state of the simulation model. And we first saw a situation for a multiple server queue where we wanted to explicitly compute things like the delay in the queue and the time in the system. And we did that by saving the arrival time and putting that into the container, which kind of did double duty. On the one hand, it provided the time that particular customers arrived, but then the size of that queue was also a surrogate for the number in the queue, which we'd been using previously. And then similarly with the Renegade model that we talked about yesterday, instead of using the times, we were using the ID of the customer in order to identify the specific customer who was leaving the queue when they happened to renege. And then the next logical thing is, well, what if we wanted to combine both of those for that Renegade model? In other words, we need the ID of each customer, and we also want their service time. Now, we could do that, but what would we have to do? We'd have to add additional we'd have to kind of connect the ID and the time, and they would be in separate containers, and then we'd have to make sure we take them both out together, et cetera, et cetera. So the conclusion from that is that, well, whenever you try to do something like that, where you have two disparate things that are handled a little bit differently, but they have to be coordinated, that is, the arrival time and the ID have to be kind of linked together. And if we're handling those differently, Murphy's law says those are going to get out of whack. So what is the solution? The solution is an object that bundles both of them together. So you all have learned maybe more than you wanted to about object-oriented design. And the thing about objects is that you can kind of stuff them with all kinds of data and have all kinds of methods, ways of getting that data out of them. And so that's what we're going to do. There is a, oops. Okay. So and these are transient entities. And okay, so what is so transient about them? Well, they're entities, objects. So they're going to represent the things in the system, like the customers. They might be a part in the queue. It might be like in a combat system. It might be a call for fire. It might be an actual unit that's moving around. It might be a sensor, whatever that thing may be. But unlike the simulation components that we have, they're essentially passive. In other words, they're like data holders, data containers. And so in the framework, they the minimum things which give you the kind of characteristics that are helpful in this context are well, and the terminology is a little different for the terminology or attributes. They call them attributes, whatever. When we implement them, they're going to be just instance variables. But some of the attributes, well, name, that's usually just that's not a vital thing because the names aren't terribly important. But things like the creation time. So when an entity gets instantiated, created, then it remembers when it was created. So that's its creation time. And so what that allows you to do is at any time in the future, like as that entity is wending its way around to the different events, at any time and point, you can say, how old are you? And how old are you? Well, what time is it now? When were you born? So I mean, like how do each of you figure out how old you are? Well, what's today? When was I born? For some of us, that's a more extensive calculation than others, but the other useful thing is a timestamp, and that's what we're going to be using. In other words, or utilizing kind of a little bit more. In other words, at certain events, we can say, remember when you were at this event. A way to think of that is, well, have you ever gone to like a parking garage? Right, most of us have. Okay, so what do you do? Well, what happens when you go in? You get a ticket, and the ticket has the time that you went in. And then what happens when you leave? You give them the ticket, and then they kind of what do? They compute. You showed up at 1 o'clock and you left at 5 o'clock. You've been here for 4 hours. It's $6 an hour, so that would be $24. So you compute how long you've been there by what time is it now? What time did you come in? So like creation time to age, whenever we stamp our time, we can get the elapsed time. That is the time since that stamp was done, just like, just sort of think parking garage. So, and now in terms of methods, it's like we think that whenever we want to stamp the time, we're going to stamp the time. So what does stamp time do? It simply sets the timestamp to whatever the sim time is. And then now this is for those of you using Python, this is kind of Java oriented. In the Python implementation, it's like the thing is with Java and the IDEs for Java, using setters and getters is important for the whole encapsulation business. Languages like Python are really not, they're really not fully object-oriented in the sense that they don't easily provide object-oriented stuff. So for the Python version, I've kind of loosened that thing a little bit. So now the names in the slides are all Java-centric. In the Python version, they're kind of Python names. So like creation time is creation _ time, lowercase, etc. And so the other thing is that in the Python entities, the getters were like Python doesn't really have sort of a get like syntax or convention. So it's just a little bit different. So those of you using Python, you just have to translate accordingly. The code will kind of show the way on that. So a simplified UML diagram, like we talked about last time, kind of looks like this. So every entity is going to have a unique ID. You know how the pattern for that works. It's going to have a name. We're going to be able to kind of call it things. That's mostly for debugging purposes, especially if we have different, in certain models, we have different types of things running around. And so it's helpful when you're debugging to kind of say, okay, here's one of these guys and one of those guys. And so we can tell the difference. but as you know, it's not rocket science. So under the hood, it saves creation time and timestamp as instance variables. And then this is again Java centric. So the Python code, the Python names are slightly different, but should be obvious. But I can get the age, the elapsed time, and stamp the time, which is to kind of do that. So we now have these entity objects that we can play with. And so what can we do with them? Well, kind of just doing this backwards, what I now want to do is now I'm going to do the multiple server queue for the umpteenth time using these entities. And then what I'm going to be asking you to do in your next computer assignment is to use this concept, but apply it to the Renegade model. So I get to do the easy one because that's my prerogative, and you have to do the hard ones. And actually, I think the model that I implemented is even slightly different. Let me just see something. Yeah, no, actually, for this is the Renegade model tweaks it even a little bit more. But okay, so let's define our model. We always start with parameters and state variables. In fact, we start with parameters. And so here, just as before, we have our usual suspects for our multiple server queue component, the number of servers and the service times. Okay, so that's very straightforward. We have our usual suspect, the number of available servers. And then we want to explicitly calculate the things like the delay in the queue and the time in the system. And as I explained last time, because these are transient state variables, in other words, they don't really exist beforehand. Like in other words, when you start up the model, for example, just to make it crystal clear, we're assuming that there are no customers. Like you open the doors of the store at the beginning, nobody's there. All the servers are available. So before the first customer shows up, is it reasonable to say how many available servers do we have? Absolutely. I mean, there they are. Is it reasonable to say how many are in the queue? Yes, because there's nobody there. But is it reasonable to say what is the delay in the queue? It isn't, because that doesn't really exist until the first customer shows up, goes in the queue, and then moves from the queue into service. So that's why these are initially not a number, because you might be tempted to set them to 0, and if you don't do anything, the default value for instance variables are going to be 0. But that's misleading, because you're saying that the delay in queue is 0, but it's not 0, it's undefined, because there is none. So that's fine. All right, so here's what it looks like. And this kind of, if you just blur your eyes a little bit, the pattern of the events should look very familiar. We have our run event, which for the server component doesn't schedule anything, but that's okay. We have an arrival event, may schedule a start service, end service, and the start service get. Okay, so the structure looks very similar. The run event simply initializes our state variables. But now let's sort of unpack the events a little bit. So here I'm going to assume that the entity, the arriving customer, the entity representing that customer is going to be created by somebody else, and they're going to pass it in. So I'm not going to be now. I mean, that's a design choice, by the way. That's not a law of nature. You could just as easily have made the arrival event have 0 arguments and instantiate the entity right here. Why do it this way instead of that way? This way is more flexible. Because I might have multiple streams of entities coming in from more than one arrival process. In fact, where that entity comes from could be something else. And in fact, at some point, we could even connect these together and have one of these entity server components have sort of the output of that. An entity that leaves that one be the one that shows up as an arrival to the next one. That is a possibility. But that's not a possibility if I create the entity inside of this. So that's just a lot of these are just a design choice. So, okay, so now what do you have to do? Well, one of the things that we want to do, because we want things like the delay in the queue, as we've seen, is the time between when they arrive and when they start service. That's how long you're in the queue. And so by stamping the time at arrival, we make sure that our time stamp is when that customer showed up to the queue. So that later, when we want to get the delay in queue, we simply get how long, what's the elapsed time. And then we want to add it to the queue. And fairly straightforward, as you might imagine in the Java version. It's going to be a sorted set, actually. And so simply add the sorted set. It's going to go to the top because the entities are sorted based upon their age by default. Okay, so then if there's a available server, we schedule start service. So let's see what start service has to do. Similar to what we have done in the previous two models, we're going to pop the first guy off. Now, in the Java version, there is no pop. Actually, we have to do a little bit of a dance, and I'll show you what that is. Just because for whatever reason, the Java sorted set, which I wanted to use for this, doesn't have a remove first. I mean, or at least it didn't. Maybe the current version does, but we have to do a little bit of a dance to first get a reference to the first one and then remove that one. That's just what we have to do in Java. In Python, there's something called heap pop, and when we get to the Python, I'll show you how to do that. Okay, we lose a server as we've done in all the other models, and now we can compute the delay in the queue as the elapsed time of that entity that we just popped off. So if we're starting empty and idle as we've always been, the first guy, this is always going to be 0. So why? Because the start service event happens immediately. But as the system goes on for a while, the queue will build up, which means that some will actually have a positive time. Okay, now notice that start service does not have a parameter. I think somebody asked about that, but it bears asking again and saying, okay, why doesn't start service have a parameter on it? It's a reasonable question. Arrival does, end service does. Why is start service getting stiffed by this? Yeah, exactly. Yeah, in other words, it's not necessary because the entity, what information do these other events need? The arrival event needs to know which entity arrived. The end service event needs to know which entity finished service, really only so it can compute the time in the system. So how does the start service know which entity it has? It's the one that pops off the queue. And you also said something very important that bears emphasizing, that the precondition for the start service event to occur is that the number of available servers, S, is bigger than 0, and that the queue is not empty. That those are the preconditions. Now, and so it bears checking that those preconditions are met. So let's look at it from the arrival event. So it's scheduled, like, in other words, if there are preconditions like that, then you want to make sure that every event that schedules it ensures that those preconditions are met. And how does it do that? There are two mechanisms for doing that. One are state transitions, and the other are conditions on the scheduling edge. So from the arrival event, if an entity has arrived and be added to the queue, then the queue is not empty at that point. It schedules start service, but only if S is bigger than 0, because it's integer. That means S is, if you were to write S bigger than equal to 1, that's equivalent. So both of the preconditions are met here by the state transition and here by the condition. At the end service event, this also does it. The state transition for the number of available servers ensures that there's at least one. And the condition assures that the queue is not empty. So again, both of those conditions are met, but where they're met is kind of flipped. So here in the state transition and here in the Boolean condition. Okay, but that's an important point, especially when you have state transitions that have the potential of putting your state space into an inadmissible place. In other words, the admissible values for the number of available servers is non-negative integers. It can be 0, but it can't be negative. There's no such thing as -1 available. It means I owe you a server. So if you're, and again, because event graphs and like all models are stupid things that do what you tell them to and not what you want them to, it is entirely possible. So a glitch, what would a glitch be? Well, if you forget to put this condition on here, then it's quite possible that you could schedule start service without the precondition of S being bigger than 0. And in that case, it'll happily execute the state transition and then go from 0 to -1. And then once your states go into inadmissible places, then all bets are off. And then just the other thing is that, in kind of somewhat verbose languages like Java, where they have getters, setters, and you have the get set sort of stuff, that's just sort of an extra, that doesn't really contribute anything. So the convention in representing those in event graphs is to pretend like they're public instance variables, which as you all know is a state of sin, but and they're not actually doing it. So when we implement this would be a call to get elapsed time, because you wouldn't be allowed to do this because that variable is private. So you can't literally do this, but you know that it's a surrogate. Okay, so that's the component. And now what can we, just as in our other two models, what can we do to make sure that we get a sequence of these customers showing up like this? Well, that's where this entity arrival process comes in. And this is the conceptual diagram for this. And it could be I've implemented it both ways, so it's, but I've come to be more and more lazy as time goes on. And so really the way to do this is that we have our arrival process, and we can sort of create a sub-event graph. I'll call it the entity arrival process. And so what it does is whenever an arrival happens, we're going to instantiate a new entity and pass that entity to an arrival event that has an argument E. In Python, Python doesn't support overloading because we have to use a slightly different name. I'll show you how that, for the Python people, I'll show you what that looks like. But basically the listener diagram is the same as what we've, the simple listener diagram. And as we've seen before, you could have multiple of the more than one of these arrival process guys listening. So they're as a side, for the sim event listening, you can listen to as many different components as you want. And likewise, a component can be listened to by more than one other component, just as the logic dictates. So, okay, so I don't want to go here. Question? Yeah. Yeah. There's the potential of that, and so you need to be a little careful. Yeah. So in this particular case, that would be kind of a dangerous thing. For the non-entity models, that's less of an issue. But it's you don't want to just kind of do it willingly in that case, because of exactly the comment was that in this particular case, if we're passing entities to more than one component, so let's say I had another one of these over here, and it was listening in, it could be doing stuff to those entities that you don't necessarily want. So yes, when it comes to entities, you want to be really careful when you have more than one component getting their hands on it. So very good point. But what I want to do now is implement this. Now, okay, so can everybody see my NetBeans? And those of you in Python can do something else for a little bit, but
yes, sir, we can see
so
it.
let's start with the entity arrival process. So here we're going to extend arrival process because Java does not overload the, it does not automatically provide the right constructors. Maybe it should, but it doesn't. So we pretty much have to write our constructor. The arrival process needs an inter-arrival time generator, but that's all we need. What we do need is, so here we're just implementing this piece. So we have the arrival event, and that's the do arrival with zero arguments. And so I call the superclass one, and this is the only time that we directly call one of these event methods. Here I'm simply instantiating an entity, and then for Java it's wait delay. I say arrival, 0 time, and pass the entity. And you see can you see that how that is still a direct implementation of just out of the box of what's going on right here. Just straightforward. Now this is actually not strictly necessary, but sometimes people get a little weird if it's not there. So here's the arrival event with the entity element. So if we're doing a strict direct implementation of this, then it's going to look like this. But it's not, this arrival event doesn't do anything. It's just meant to be heard. Okay, so let's look at the server. So here's the entity server. So what do we have? We have our two parameters, the total number of servers and the service time generator. Those in Java, those are going to be private. Our state variables are protected. And so we have the number of available servers, the queue. Here, I'm counting the number served as well. It isn't strictly necessary, but I'm going to do it anyway. Delay. Now, here's the delay in the queue and the time in the system. And this is where declaring these. I know that some of you like to initialize your instance variables where you're at the declaration. And in the Java class, that was sort of I'd only complain about it. Here, you really don't want to do that. You don't want to do that because the parameters are going to be passed in. The parameter is going to be set from the outside. So there's no reasonable implementation inside the component, for example, of the service time generator. It's some random variable. And so whoever is going to run a model and use this component is going to have to tell me which random variable they want to use. Which one, if I want to put a default one, which one should I do? I don't know. I mean, there is no logical one for that. And likewise, what default total number of servers would I have? Well, the default instance variable is 0. And if I have a server component with 0 total number of servers, how is it going to behave? Nobody's ever going to get, I mean, the queues, basically it's like everybody's lining up at a store that's permanently closed. So the queue, it's just going to go nowhere. So the default makes no sense. Okay, so now here there are a couple of options on this, and it depends on how green you want to be. So what I'm doing here is the state variable Q is going to be it's declared to be a sorted set. I'm going to instantiate it as a tree set, but I'm going to instantiate it in the 0 argument constructor and then call it from this in the master constructor. Why? Because I need to make sure that this is always going to be instantiated. Now, I don't have to do that. If I instantiate it here, then what I'm going to have to do down when I reset them is I'm going to have to, instead of clearing it, I'm going to have to instantiate a new one. 6 of one, half dozen of the other. And I think in the Python version, that's what I wound up doing just because it was, I don't know. Anyway, okay, so this convention is this. You have 2 constructors in this Java version. And a 0 argument constructor, and the reason for that has to do with something that we'll talk about later in the course, maybe. But the master constructor has a list of all the parameters because all the parameters have to be set by somebody else. And what that should do is simply call the setters. The extra little thing about that is, again, remember I mentioned that the total number of servers needs to be 1 or bigger. Otherwise, if it's, obviously negative total number of servers makes no sense, but the language doesn't, there's no such thing as a positive integer. It would be nice if there were, but there isn't. All we have is an int. We could be plus, minus, or 0. But if it's 0 or less, then we know that this component is going to be useless. And so if we try to set one with an invalid value, we want to throw an illegal argument exception. And we're going to do something similar in the Python one. But now let's just sort of look at the events. Okay, the run event. Clear the here. Okay, so the run event, we're just basically going to clear the queue and set everything equal. Oops. And so the run event is the reset. The method is where we do these the initialization, and the do run method is where we do the scheduling and the property changes for our initialization. So in this case, because it's not scheduling, the do run method only fires the property change, and in the Python version, it will only notify the state changes in a similar manner. So now here's the little dance that we have to do with the arrival. So we do need to stamp the time and then add it to the queue. And it's important to do that, again, just because of the way that Java works, we need to stamp the time before we put it on the queue. Now this is, now in the Java version, we do the old value, new value dance. The Python version, we don't because it was a little too much overhead. So, but here's where, if you remember last quarter, for those of you in the Java class, whenever we have a getter that's a container or an array for that matter, we never want to just return a reference to the thing itself. We want to return a new copy. And that's it. And you have to, even though the setter for this we can generate using the refactor, encapsulate fields things, I needed to actually put this in. And if you don't do that, then strange things happen. Here, okay. So stamp the time and add it, and then fire the property change using the getter. Okay, so this is exactly the same as we've done for a long time. Now, at the start service event, we have to do something a little different. Now, this is the same as what you did for the simple server component. But here's the dance that we have to do. First, we want to save the old one, but then we have to implement pop. We need to first get a reference to the first guy and then remove that guy. Why they don't have a remove first one, I don't know. And maybe they've added one since I haven't, maybe I should check that. But this will always work, but it is kind of necessary, unfortunately. Okay, but now we can get the elapsed time from our entity. That's our delay in queue. We can fire that. And the end service, very similar. Now directly, oh, why did I do it that way? Actually, their hint is actually a good idea. And it actually matches the event graph a little bit more. So if it's not empty, I'm going to schedule a start service. And that's the whole thing. So now when I run it, now this is what, because we can now directly compute those delays in queue and times in the system, we can now use Little's formula and see how well it does. Okay, remember as you've seen, at least numerically, whenever the system is empty, Little's formula holds exactly. What is that? That's the relationship between the time average of the number in whatever piece of the system you're interested in, and times the arrival rate, and that's equal to the average time in that when it's empty. And the claim is that if we run it for a while, they will be approximately the same. So let's run it for a while and see if that holds up. Maybe it does. Okay, so here's now setting this all up. This is all something that you've kind of done similarly. You've all done the simple server component, so it's basically like that, except that we have our entity arrival process going. We have our and I'm going to call it entity server, okay, instead of simple server. Yeah. So now, and we want to collect statistics. So you all did that on the last one using the time varying one. And so for the number of available servers, we have simple stats time varying, which we can use. But what about the queue? So now the problem is this simple stats time varying is looking for a number. And what we were firing a property change with the queue, which is a sorted set. Okay, so how can we deal with that? Well, there's another stats class called collection size time varying, which is attempting by its name to show what it does. And it will listen for a collection, but do a time average of the size of the collection size. And so that's what we want to have listening to our queue. And then for the delays in queue and the time in the system, those are now tallies. And so we don't want to compute those using a time average. We want to compute those using a straightforward tally. What does simple stats tally do? Simple stats tally basically does the same thing as the class that you wrote last time about I forget forget what we call it, simple stats or something like that. And then we just add these all to as a property change listener. And then what they're going to do is, see, when I say delay in queue, this is each of these is actually going to hear all of the different state changes. But the way they're written is that if, for example, if this simple stats tally here's something, here's a state delay in queue, it says, oh, that's one of mine. If it hears any other state, it says, la, 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 la. I don't hear you. So let's see, I'll round it for 100,000 time units. We'll stop at that time, and then just sort of do the computations. So the computations are very straightforward. This is, you can pull this from the class code. So again, always print out your sim entity base objects just to make sure that they've gotten the parameters right. Okay, so we ended at the right time. We've had this many arrivals, this many served. So average number in the queue, 15 whatever, utilization, average arrival rate. And now let's look at little here. So our average delay in queue from the tally was this 24 point something. And from little, it was 24.7622. So it was off in the 4th decimal place, which is pretty close after 60,000 observations. And similarly, the time in the system, 27.8092 versus 27.8080. Again, so it's off in the 3rd decimal place, again, out of this many observations. Again, doesn't prove anything. You know, in order to, you can mathematically prove this thing about Little's formula. You need some additional assumptions, and it takes about 10 pages of mathematics. And so we could spend the rest of the quarter on that, or we could actually do something with it and say, okay, here we at least have some, you've seen 2 instances, actually 3, including the demonstrations that I have. So we did one by hand where we showed that it held. You did one by hand where you showed that it held. We've now run one on the computer for a long period of time that shows that it approximately holds. And so it's a reasonable thing to believe. Okay, so I'm not making any assertions that I've successfully proved it, but it's true. Okay, so let's look at the now the Java folk can kind of relax a little bit. I do want to do this for Python. Don't want to leave those guys out. So, okay, that is kind of okay. So in the class code for Python, in the MV3302 classes one, again, toward the bottom, we have the entity arrival process, which subclasses arrival process, just as we had done. Now this is a little bit different, but pretty much the same as we've done previously. So we pass in the inter-arrival time generator, and then we have to pass that to the init, the constructor of the superclass, just to make sure that works. And then just as, because it's the same thing. Oops, here. We're just implementing this piece right here. We have the arrival event. We want to instantiate an entity and schedule. Now, the event graph says arrivals, but in Python, we have to do something else. So what do? We do we'd have to invoke the superclass arrival event to make sure that happens. And now we're going to schedule, I'm going to call it entity arrival because I can't call it arrival. So let's look at the entity server. Now, just as with the basic one, we have the total number of service and the service time generator. And so we pass those in to the init constructor and then pass ourself to the superclass constructor, which is SymEntity based in this case. And now we take these and we set them equal to our instance variables, the total number of servers and the service time generator. As you may have noticed, my convention is I use the same name in both of those. And if you're not comfortable with that, you can use a different name. That's not a law there. So now here's where it's a little different. I'm initializing my state variables to not a number, and even the queue, I'm initializing it to none. Why? I don't know. Because in the reset method, which is the run version of the state transitions, here I'm just instantiating a whole new array for this, setting the number of available servers to the total to begin with, and then not a number for our other two. So our run event, I'm only notifying state changes for the states that are not a number. So let's look at entity arrival. That's sort of the key thing here. Okay, so the entity arrival method event has an entity as its argument, and so here's the entity that we're passing in. Just as before, we stamped the time, so here it's done as a method, but in a sort of a Python underscore lowercase thing. And then, so here's how we don't want to use the array as an array. We want to use it as a sorted set. The way to do that is using something called heap push. And this is, notice that this is a function. And so this is very non-object oriented. So when I complain that Python isn't really object oriented, this is an example of it. So, but you want to use a heap push because that's going to keep the entities in the sorted order. And we notify our state change about the queue. If we have available servers, we schedule those. And now for the start service event, okay, here it says pop, but in Python, it's called heap pop. And again, is a function, not an instance method, which it should be, but that's, you see, if Python were truly object-oriented, then it would not be a function, it would be an instance method. But that's how we pop it off and get our entity. We can compute our delay in queue by our elapsed time. And in Python, they don't have the get convention, they just have the name convention. So we're just following that. And then we schedule the end service. And all of that is pretty much the same. So in the run method, let's kind of run it. We need to do pretty much the same thing as we did before. So here's our inter-arrival time generator. We instantiate our entity arrival process as that, and then I need this extra describe method just for, it was a Python weirdity that, or maybe my weirdity that I couldn't figure out how to do it in Python. So, and then service time generator there. And then it has a similar set of statistical objects. So there's a simple stats tally, a simple stats time varying, and a collection size time varying. They do the same things as the other ones do. The simple stats tally will receive values. It'll hear values from a notify state change, add them up, divide by the number. That's how it does the mean. The time varying computes the area under the curve. And then the collection one will hear a collection and do a time varying calculation based upon the size. So we're gonna, after running it in verbose mode and testing it out, we'll run it for 100,000 time units. and then do all the same calculations as before, trying to figure out whether or not the extent to which Little's formula holds or not. Now, just one of the other, okay, so we've had about 60-some thousand arrivals. And the numbers are a bit different, but you know, that's sort of to be expected. But let's just sort of check Little here. So by a direct calculation, we have like 48.75. Using Little's, we have 48.74. Similar for the time in the system, we have 51.82 and 51.80. So it's a little bit more off. I think I need to do a little more check. I'm for the random variates, I'm actually using things that are in Python, and some of them I find a little suspicious, but nevertheless, we see whether it's Java or Python, Little's formula seems to be holding up. And now you know how to do entities with this. And for tomorrow, it'll be the next computer assignment will be posted later today. But it'll be now doing something similar, but for the Renegade model. Okay, any questions? I went a little bit over. My apologies. I owe you 2 minutes.